this is my data, not your data, so don't copy my data down. Unless you were not here and you're watching the video, then you can copy my data down. But would you expect my data, to be exactly the same as yours? No. Should it be semi-close? Yes. Okay, semi-close, right? But we're measuring with M&Ms. There's a lot of room for error, right? But we're going to start by looking at some of our graphs. We're going to talk through all this data and talk through a bunch of stuff. So if you weren't here, or a reminder if you were here, we had circles. We measured the diameter, the circumference, and the area with M&Ms. And then we did a little probability activity down there at the bottom. All right, so let's see. So I want you to look at your first graph, what you plotted. And I think that you're supposed to, based on your scatter plot, right, just looking at the graph, what do you think is most appropriate? Now, I think some of y'all's had a little bit of a curve to it, which is possible just based on your data. It's also possible because we're graphing on something that's not really even a grid and having to estimate. So maybe it doesn't really have a curve, but the way you graphed it does, totally fine, right? But I think most of us agreed that we think this should be what? Linear, okay? Now, let's look back at our data. So flip it back over and look at your data for this one. We've looked at a lot of data tables and tried to decide if it was linear, quadratic, or exponential, or whatever. And so if it's linear, the data is linear, then we would expect our first differences to be the same, right? Be constant. So I want you with yours to find your first differences here. Okay? So find whatever yours are. And our differences wouldn't be exactly the same as each other either. But for mine anyway, mine are not constant. Are any of y'all's constant? Okay, and with real data, like real live data, we don't necessarily expect them to be exact, but they should be pretty darn close. Mine aren't even pretty darn close to each other. The first three are, but then it goes off the rails, right? But that doesn't mean that we're wrong about it being linear. What did we not look at that we should always look at first? What about the x? What do we need? And what do we need the differences in the x to be? Constant. We need equal length input value intervals, right? That's why we look at that first every single time, because we don't have equal length. This is 1.5, this is 1, this is 2, this is 4, this is 2. So I don't have equal length input value intervals. Since I don't have that, my first differences don't mean anything. Even if my first differences were constant, that definitely wouldn't tell me it's linear because I don't have equal length input value intervals. Now, for linear, I could actually then find my rates of change and put 4 over 1.5, 5 over 1, and do all that. Then those should be semi-close, right? But we're not doing that anyway. I mean, it asked us to look at it and just look at the scatter plot. But I just wanted to point out this is why we look at equal length input value intervals. You can't really look at your differences here, okay? But if we're still like, well, we think it's linear, or maybe you thought yours might be quadratic or something because yours had a curve to it, let's talk about how we would actually know for sure before we actually do anything. What is the formula for the circumference of a circle? 2 pi what? R. Okay. So circumference is 2 pi r. Or I could write that circumference is what? What's the other one? Pi times what? Diameter. Okay. And they're both, they're both totally fine. But if I want to talk about the circumference as a function, because we found diameter, right? The circumference as a function of the diameter, I can write it like this. Okay? That's circumference as a function of the diameter. That is my function notation, right? So that is a function there. I could rewrite this in terms of x and y as y equals pi times x. Then when I look at this as an equation that I could graph, then this is, what kind of equation is that? It's linear. because it's y equals m times x, and then my b is just 0, right? My slope here is pi. Does that make sense? So this is a linear equation, therefore I know for sure that it is linear. Okay, we good with that? All right, now you should already have yours written down here. I'm going to write mine down. And we'll talk about them. Okay. So I would expect that your equation would be pretty close to mine. Now, your y-intercept, it might be minus instead of plus, but it should be a very small number, pretty close to 0. Do we all have pretty small y-intercepts? So let's think about why that is. If my diameter is 0, what would my circumference be? 0, right? So your line should go through 0, 0. That's why this is like plus 0 here, right? We don't even have that. Now, because we have real data, we were measuring with unknowns, it shows that we actually don't go through 0, 0, but we're pretty close, right? Which is fine. Also, your slope right here is pi. Is your slope kind of close to pi? At least 3-ish, right? So this is kind of pi-ish, right? Because pi is about 3.14159, blah, blah, blah. Do any of y'all know tons of digits of pi? Somebody want to tell us? Like, can you give me like 50 digits? Can you? How many of you know? Like 40? You want to do it? Okay. Dang. God bless your brain. Anybody else want to do it? No. So, can you do it backwards? So 1 year I had 2 students that we used to go to homeroom every day. Y'all think homeroom's torture now. Can you imagine going every day and having nothing to do? Yeah. So there was a lot of nothing to do in homeroom. But they had a math teacher for homeroom, and she had the pi digits around the top of the room. And so because they had a whole lot of nothing to do, they would just basically stare at it. I don't even think they tried to learn it. They just stared at it, and then they knew it, right? So they both knew, because there was 50 digits. They both knew 50 digits, and they rattled them off. And then one of them, somebody goes, he can do it backwards. And he said those 50 digits backwards. I put it on the board so I really don't know how my brain definitely doesn't work that way, but very good. Did you just learn it for fun? Was it a challenge? Was it okay, very cool. All right, so 3.14159, blah, 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 26 something. I don't know. I don't necessarily know anymore. There's a song I can sing, I know a little bit more, but it's fine. But anyway, so do you understand the connections here then? Right, we good? Okay. We're going to come back and do some more with that in just a little bit. So now let's look at this one. Now on this one, y'all had, some people had quadratic, some people had exponential, some people were having discussions at their group about which one they thought it should be. And really, I think if you're going by the way this looks, you could argue either way, right? And I think I even came around to some of your tables and said, well, don't you agree that some exponential functions can look like half of a parabola, right? So you not being able to tell by looking with just minimal data makes sense, right? If I had more data points, maybe it would be more obvious. So I told you to go ahead and find both of them and write them both down. But let's talk about how we can figure out exactly what it is before we even worry about choosing our model. And it's not necessarily what looks best in the calculator, because your data may not be perfect, right? So what is the area formula for a circle? Pi r squared, okay? And then we know that the diameter is 2 times the radius, right? Things that we know. Then I also know that I could say that the radius is equal to the diameter over 2. Okay. Everybody agree with all that? Now I'm going to take this and substitute it in where r is here. So this is going to give me pi times d over 2 squared. So when I square the d over 2, what does that give me? D squared over 4. That was a lot rougher than that should have been, guys. That is not difficult at all. I could rewrite that as pi fourths times diameter squared. So just like with circumference, where we had a radius formula and a diameter formula, we actually have both for area as well. We just don't really talk about the diameter one much, because It's not something people would easily remember, and it's just way easier to do that because you can just take half the diameter. But that's your area formula. If I did that in terms of x and y, that would be y equals pi fourths times x squared. What kind of equation is that? That is quadratic. So of the two that you have written down there, circle your quadratic one. You can just leave the exponential one, but it's quadratic is what's happening there. And I did hear some good discussion at some point yesterday. Somebody was, I don't think, very nicely talking to their group, but said the other, we've looked at data tables, but then there's another way to tell if they are linear, quadratic, or x or cubic, I think is what we were talking about then. And the person that was semi-yelling at their group said, well, what is this about? This is about area, so what do you think it is? But remember, that's one of the ways to talk about the fact that it's quadratic. If it involves area, if it involves volume, it's cubic, that sort of thing, right? So the fact that it's area should hopefully make you think quadratic as well. But again, I understand why looking at the data or looking at these points would make you think it could possibly be exponential. But it is definitely quadratic. So let me write down my equation that I have. Okay. So I have 3 terms to my quadratic. Do any of you not have 3 terms? Okay, because I think last year I had one group that ended up with 2 terms, which is definitely a possibility. But I'm really only supposed to have 1 term, right? If my diameter is 0, what is my area? 0. 0. So this should go through 0, 0 as well. If it goes through 0, 0, then I don't have any translations, right? This right here tells me I do have translations. If this was in a form where we could pick out our transformations, it would be factored and we'd have like a plus k and all that stuff. But if I multiply all that out, think about this as the multiplied out version, and that's why I get my 3 terms. And so there's a little bit of a transformation, even though there shouldn't be any, but that's because, again, we're measuring with M&Ms. There is something called a power function. Those words may have never been used with you before, but I want to explain to you what it is. So we have polynomials, right? It could be x squared, x cubed, x to the 7th, whatever. But a power function is when you have just one term like this to some exponent. So it's a times x to the nth power. That's what a power function is, meaning that there are no transformations. I'm sorry, there's no translations. There could be a vertical dilation, but that would be the only transformation that there is. So there, I couldn't figure out in Desmos. Of course, I didn't check again this year, and maybe they've updated things. There is a power regression in there, but it still doesn't force it into what I wanted to force it into an x squared with my data. And so I'm going to write down what mine is, and you can write that down too. And then I'm going to tell you why it matters, why we even care. So if I force this into just an x squared power function, this is what I got. 0.7939 times x squared. Okay. Using my data, that's the power function. Okay. So like big whoop, right? What does that? Why do we even care? Well, because here, where I have pi fourths times x squared, pi fourths as a decimal is about 0.7853. So look at that number compared to my number. That's pretty darn close, right? And I think just like your slope being kind of close to pi, if we could force y'all's, which is, again, it's not an easy, quick thing to do with the ways I know how to do it anyway, yours would be probably pretty close to that 0.7 number as well. Okay. And by the way, my data, I didn't copy it down from like an answer key or anything. I actually did this activity just like you did, so who knows how good or bad. I mean, I tried to be very careful with everything, but it still may not be perfect. Okay. Everybody good so far? All right, so then your last one, even though there was some discussion about whether or not we thought it was quadratic or exponential, I think most of us decided it was probably exponential. Okay, so let's talk about why we would know which one it is before we even get started. There's something called theoretical probability and experimental probability. If you flip a coin, what's the probability it's going to land on heads? 50% or 1/2, or you got a 50-50 shot, right? If I flip a coin 10 times, my theoretical probability is I should get 5 heads and 5 tails, right? Am I guaranteed to get that? No, because if I actually do it, that's my experimental probability, right? So when we drop to the 100 M&Ms, theoretically, how many survivors should we have had first? 50. And then the second time, 25, right? And keep going like that. Now, did anybody get exactly 50? No. But if look at your data, mine's kind of close, right? I mean, I got 54 and then 26. I mean, but then I got 6, 3, and 3, and nothing changed down there. Take your hood off your head. That's what I was saying, which I shouldn't have to say. And did anybody? Is it possible? Would it have been possible for you to drop 100, all 100, and have 100 survivors? Is that possible? Yes. Is it probable? No. So those are two words that are very important with statistics. A lot of things are possible, but it's definitely not probable, right? I wouldn't have wagered any money on that type of thing, right? That's definitely not. Even though, yes, it could totally happen. How many did any of y'all get more than 54 survivors the first time? What did y'all get? 60. How many did y'all have? 56. Anybody? What did y'all get? 56. Okay. I forgot. I didn't even think to ask earlier today, but 60. I mean, so it's still, close to 50, right? It's kind of what you expect, but again, not necessarily perfect. Some people ended up with 0 on the fourth one, and it was 0, 0, 0. That group back there had one blue M&M in their mix, and I think it showed up last period yesterday. And so those people, they used it in their drop, and that blue M&M survived until the last two M&Ms. So think about what that probability was for that guy to survive so long. That's a whole different type of probability situation. And then I think when y'all did it, it was out, what, in the second round? Yeah. Then he was out quickly there. So I think next year I'm going to throw a random color in each one, and we'll just kind of look at that too, just for the heck of it, because I don't know, it's kind of interesting, right? All right, but so let's go back over here. Because of that, because I know each time I do it, I would expect for the number to get cut in half, right? So that definitely sounds like a geometric sequence to me. And so if we think about exponential, y equals a times b to the x, what does a represent? Your initial amount. And what do we start with? 100, okay? And then we expect it to be cut in half each time, so that would be times 1/2 to the x power. Okay, so that is your theoretical equation. My equation from the experimental side was this, so hopefully you have yours written down. So this represents A, and this represents B. So is your A value kind of close to 100? Yes. And is your B value kind of close to 0.5? Yes. Okay, and it should be. Now, the other two graphs we did, if yours was farther off or not so great, that had to do with how accurately we were measuring. But again, it was with M&Ms. It's all good. Here, this has nothing to do with accuracy. This is just, what actually happened when you drop the M&Ms. There's no skill involved here at all. All right, so now what I want you to do in Desmos, because we went there and then your computers probably turned themselves off. But in Desmos, I know you already have the equation, but I want you to go back in there and all of you type in your survivor data back into Desmos in a table and find this again. It won't kill you, I promise. Remember, yours should be green at the top. Mine is black because I cheated and I saved it. I can't save it in the other one so that I didn't have to type this in 1,000 times and take forever. Yes, exponential. So go ahead and do your exponential regression. How come there's what? Yeah. Okay. So what you should have is your equation that you already have, right? Good job. That's it. And because you should be in the green one, your log mode should be checked. Do any of you not have a log mode? Okay. So we got two groups that don't have a log mode. All right. So if you don't have a log mode thing to check, that is telling you that the log mode version is the best version. Okay. If you do have a log mode, remember, for AP purposes, or really for any purpose unless you're told otherwise, you want it checked. Because honestly, I don't even know when you would use the non-log mode. So I'm assuming probably in like a higher level statistics class or something. I don't even have the first clue, to be honest with you. But what I want you to do on yours, so whatever's the log, that's what you should have written down. If you have a button, if you don't, that's okay. We'll talk about that in a second. Then unclick it, and now you have another equation. So over here, write that this is my log one, and then write your non-log one here also. And then we're going to talk about the differences. So those of you that didn't have the log mode button there, was your A value closer to 100 than mine? Is that like, what is your A value? 101, what's your A value? 107, okay. And then your B value, I would imagine is probably closer to 0.5 than mine is, okay? But then the rest of you that had the log button, when you look at my non-log, way closer to 100 than that is, and way closer to 0.5. Is that true for the rest of you? Okay. So what it's telling you is, and again, we're going to look at the R values just because we can. We, if for the purposes of this class, are not using the R values to actually figure out anything. I'm just showing you how this stuff works because, it doesn't kill you to learn some other things. But for when I'm not in log mode, the one that looks closer to what I know it should be, my R squared is 0.9985. When I have it in log mode, it's 0.9756. So that tells me that this one is better or closer to what we would expect. But remember, they're calculated in different ways. If you were to use a handheld calculator or anything else that y'all have access to besides Desmos, it would be log mode, okay? Because most people probably can't even explain. I have to read this little question mark every time to make it make sense to me again. So always make sure it's checked. I just wanted to kind of show you some different things here, okay? Everybody good so far? What's the question mark? It explains log mode. Oh, you don't have it? Oh, that's probably because I'm in a different version. So it doesn't matter. All right. So now what I want you to do, I want everybody to go to Canvas. Count yourselves off, 1 through whatever, at your tables. Nobody should be clicked into any kind of Google sheet right now. Some of y'all are way ahead of me and doing the wrong thing. You should be in Canvas. Find the assignment that says M&M data. Click into the assignment. Do not click any of the links in the assignment. Okay. All right. Are we all counted off at our groups? 1, 2, 3, 4, or 1, 2, 3, or 1, 2, 3, 4, 5, whatever. Everybody have a number? We'll make it happen. Okay. Nobody click anything yet. But in a minute, some people are going to click this, click a link that will get you here, but nobody should be there yet. All right. This is my data with my equation. There's a spot over here for different groups to put in their data. I will give you a group number in just a second, okay? But only one person from your group is actually typing in here. Nobody should be typing in the area or the survivors yet either. Because what we're going to do is we're going to watch this kind of change to see if it gets better, see if it gets worse, just kind of see what's going on with our data. When you're typing and you get to your last little cell, you have to hit enter to get out of it, right? Somebody sitting next to whoever's going to type this stuff in might want to be double checking that they're typing in the correct numbers. Some people are typing challenged. All right, so if you are number 1 at your table, raise your hand. Number 1. Okay, y'all don't have a number 1 back there? Who's number 1 back there? Did y'all not count off? What is your problem? Who's number 1? Okay, thank you. All right, number 1. All right, number 1, pick somebody at your table to type in the circumference data. Okay. And then that person, click on circumference, go into here, start typing in your group's data for the circumference. Okay? Knock yourself out. Do y'all understand the assignment? Okay. Oh, you need group numbers. Thank you very much. You're like, yeah, we understand. We don't know what group we're on. 1, 2, 3, 4, 5, 6, 7. Okay. Yeah, the top one, the circumference one. And then yeah. I just want to say I was very proud of myself for figuring out how to do this in Google Sheets. If you do it all the time, you're probably like, it's really not that big a deal. It's a big deal if you have absolutely no idea what you're doing, but I did make some pretty cool graphs. I learned a lot. But we expect our slope to be pretty close to pi, right? Yeah, it's okay. Somebody typed something wrong. They'll fix it. See? It's all good. It's all good. All right, take a deep breath. We're fine. We're fine. All right, group 4, make sure you click out of that last cell. I know, because if you have it typed, you can see it, but nobody else can see it. There we go. All right, so here's what we got now. We're at 3.19, which is semi-close to pi, right? Do you think that there's maybe a couple outliers here? Yes, okay, so no judgment on anybody, because again, we were measuring with M&Ms, right? Although one of them, I did give you the diameter for the first one. So I don't know whose number, again, no judgment. I don't care whose it is, but whoever, that when you have 1, 5, take that point out. Okay. And then, I mean, we were all pretty stacked right there, just perfect, right? These diameters are kind of spread out, but this guy, I mean, he's not a true outlier. Did y'all actually take that one out? Whose is that? Oh, did you delete it? Oh no, it's the green one. You have to hit who's group for. Well, you didn't have to change it. I just wanted you to take it out. Now you're cheating. 717, whoever's that is, take that one out. Just because it's kind of different from the rest. Probably not really a true outlier. Outlier would have to be pretty far out there. Just delete that out of there so we can see how the graph changes. That actually made it farther away from pi, right? So taking out some outliers doesn't necessarily always help you. But that's still pi-ish, right? Close enough. We have a very small y-intercept. If we had everybody's data from all day, because even though we have 8 sets of data here, that's still not a ton. If we put everybody's together, that would make it better and better and better as we go. Okay, we all good on that? Huh? Well, that's our class equation. We don't have to write it down or anything. All right, so then just look at this before anybody does anything. Here I have this as a power function, but I couldn't force it to be x squared. There's a power regression. So notice my exponent is not 2. It's 2.04, which is really close to 2. But because this isn't exactly 2, it makes this number farther away from the 0.78 number, because mine was closer than that. So this might not be super close to 0.78 because we can't force that to be 2. But who knows? It might work out beautifully. Let's see. So number 2s, raise your hand. Okay, now pick somebody at your table other than the person that just typed in to type in your area. And y'all go type in your area. Yeah, same group numbers, yes. Same groups, yes. Group 5, group 7, do we understand the assignment? Are you the one that's supposed to be typing? Okay, okay, no, I'm just making sure. Because I was like, if y'all picked him, pick somebody else so we're not waiting for him. All right, group 7, do we know who's supposed to be typing? Just making sure that, okay. Because one period, I was sitting here waiting, and then they were like, I'm not number 2, you're number 2. What do you, and then I was just somebody typing the data. Yeah, exactly. group 3, you got to hit enter on your last. Okay, and then how are we doing with 7? All right. So as we look at this, that's pretty close to 2 and pretty close to the 0.78, but that actually should be a little bit different just because it's not there. Would you say there's some true outliers here? Yes, I think that there's 2 true outliers here. And it could be that we type something different. It could just be that who knows, right? But I think most everybody decided that the diameter was 12 here. These people, and again, I don't no judgment. We were measuring with M&Ms. But whoever has that 14,113, take that out for me. It's okay. All right, and then whoever has the this one, the 1263, take that one out too. Somebody? Anybody? I'll, I'll call you out if I have to. Who had the 1268 or 1263? That's group 4. 1263. There we go. Okay, just takes a second. All right, so now look, we are super close to 2 and pretty close to 0.78, right? Which is what we were expecting, but we do expect this to be a little bit lower because that's a little bit bigger than 2. But just a couple little outliers can kind of, affect things big time. With real data, you don't always get to just like get your outliers out of there. But again, we were all pretty much there, but we're pretty clustered together. Things look pretty decent. Okay. Now, before we choose who's doing the survivors, I want you to look at this because we're going to look at this one a little bit closer. Oh, shoot. Did y'all actually type stuff in already? Okay. All right. So I think maybe I forgot to delete that out. So y'all didn't already type stuff in, right? Okay. So it's second period. That's why. Jeez, thank you. I was like, what the heck? Who's typing? Yell at y'all. I was like, I really thought I deleted all the data. All right, so what I wanted you to see here. So here's my data, right? And my equation, but what does this equation have in it that none of us did? E, okay? And we're going to look at that. It's going to look a little bit different at first, but then we're going to see how it's actually the same. So raise your hand if you're number 3. Okay. Pick somebody that hasn't typed yet to type in the survivor data. And make sure you type in the 100 because y'all didn't have to write it down. It was already typed in. But we're going to watch this. Y'all are fine. Group 3 just hasn't even started. Who's group 3? Now, on the first 2 graphs, accuracy played a part in it, right? But again, we were measuring with M&Ms. Accuracy has nothing to do with this because this was just literally what happened with our experiment. Group 2 hit enter, so it takes that cell. There we go. Okay, just making sure we're all good to go here. Okay, so now we have this. We have 102 times e to the negative 0.716. I need to write that down because I need to write it down again. And 102. Okay. So I want us all on here to write down that equation, which I'll write back up here. It was y equals 102 times e to the negative 0.716 x power. Okay, so that's what we got as a class from our little experiment. This 102, this is your A, right? Which is close to 100. which is a lot closer to 100 than what I had, and maybe closer to 100 than what at least some of us had, because some of y'all were really close on that. But then we have this E thing, right? So what we've been doing to get equivalent forms is undoing the power to a power property. So if I have 102 times e to the negative 0.716 power to the x power, right? That's an equivalent form. That was literally on our last notes and on your assignment. I don't think there was an e in there, but it doesn't matter. So this represents your A. This represents your B. Okay, so B is equal to e to the negative 0.716 power. And then somebody type into Desmos e to the negative 0.716 power. I want to know what that is as a decimal. .44? 88. Oh, that's interesting. That's what it was last period too. Last period was like 0.488 something. Which is, that's right here. That's your B. That's pretty close to 0.5, right? Might be a little farther off than what you had, but it's actually a little closer than what I had. But just on the other side of the 0.5 there. Okay. But that's why the equivalent forms, we can actually put it into this form right here and not have a horizontal dilation there. Okay. The reason I had second periods up, I didn't realize that's what I clicked on, but I wanted to show you because this is the only one. I've done this multiple times, like for multiple years, but I think this is the first one in this class where we actually got 100. And what is, somebody do e to the negative 0.664, because I think that was even closer to 0.514, which is really close. Like this was probably like the most accurate that I've gotten, but accurate theoretically, right? Because it's experimental, anything is going to happen. I mean, look at the second one. They're all really grouped together. We all kind of got the same thing there. But. All right, questions. So I wanted to connect these functions to actual formulas that you know, talk about your data, talk about regression. Tomorrow we're going to start 2.6, which this leads us into, to actually pick good models and whatnot. So go ahead and put this in your ISN.